Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Sempai.
Welcome back, everyone. Today we're jumping into a 12th grade topic, finding your trig limits as x goes to infinity. Now, if you're new to my channel, I'll be putting time codes in for this video in the description box below, so use it to skip ahead to whatever part of the video you think is most interesting. As always, if you have any questions about what you see today or even on homework, you can always put in the comment box below or visit my Facebook page at Tutor Me Sempai and tell me all about it there. At the end of this video, I'll be linking my 12th grade playlist, in which I cover a lot more topics. So if you're interested in that, make sure you stay tuned. This video is only going to have 3 parts, so leave a like, smash the subscribe button, and let's get started! Now, when you're trying to find the limits of your trig functions as x goes to infinity for your basic trig functions like these, the answer is actually going to be fairly obvious if you think about how trig functions react, how they behave as x goes to infinity via the graph. Remember, your trig functions are going to be oscillating every period. They go from one period to the next, repeating the same exact thing. That means as x goes very, very, very large, as x gets closer and closer to infinity, right? It's going to do the same exact thing. Repeat, and repeat. That means we're not approaching any particular number. Thus, the limit of sine as x goes to infinity is just going to be does not exist, actually, because it doesn't approach any one number. Same thing for your cosine. It doesn't approach any one number. Every period, it repeats itself. That means it's not going to have a limit. And this is going to be true for all your basic trig functions. But of course, not all trig functions are going to fall into this category. Let's move on to our next section, which you're going to have to do a little bit more work. Let's say you have a function that looks like this. You have sine of x over x. And we want to find a limit as x goes to infinity. Now, if you've been with me on this channel for a little bit, you may think that we have done this already. This looked very similar to something we actually did talk about. However, the limit was a little bit different. It was, in fact, as x goes to 0 of the same function. And we said that this is always going to be 1. We know that to be true, and we use that to find other limits. But you would be mistaken if you're going to assume the same thing is true about this limit. This is actually not going to be 1 because it's not the same limit as that. In fact, in order to find this limit, we're going to use the squeeze theorem. Now, on the channel, we've talked about the squeeze theorem. If you missed it, no worries. You can find it right up here. But the first thing you want to do for a squeeze theorem is find the bounds for your function. But we're not going to find the bounds of this. We're going to do a basic version of this function and build until we get to this. So we have a trig function, sine of x, and we're going to start there. And we know that sine has bounds. It's bounded between -1 and 1. Now, we are going to divide everything by x. Everything by x. Now, when you do that, you realize x can be positive and negative. So you may be thinking, well, if x is negative, we got to do some stuff with the inequality. But in this case, you don't have to worry about it, because if you think about it, if x is negative, this becomes positive, right? So this becomes positive, a positive number. You would then swap that sign. This would become a negative number, and you would swap that sign. And of course, it stays the same. And you notice it's the same exact thing. You have negative less than or equal to sine of x over x, less than or equal to a positive number. And it's the same thing, just in reverse. So we can save ourselves the headache and not worry about switching these signs, because it's not going to make a big deal for this particular example. So we're going to divide everything by x. Next, we move on to finding out if the bounds that we just found have the same limits. So we're going to find a limit of everything, right? So we have the limit as x goes to infinity. Because the squeeze theorem, you can go to infinity. You don't have to just go to a particular point. You can actually go to infinity as well. So we're going to do the squeeze theorem here. Now, what's the limit of -1 over x as x goes to infinity? We also talked about this on this channel. If you missed that, no worries. It's also going to be right up here if you need it. But we know that this limit is actually going to be 0. And that's going to be true whether it was a -1 up top or a +1. They're both going to go to 0 as x gets very, very, very large. So that means the limit does in fact equal each other. Our squeeze theorem then tells us that because we're bounded and we know that the limits of those bounds equal each other, our function has the same exact limit as x goes to infinity. So you see, this is not the same as that limit. Don't get confused. This is x goes to 0. It's going to be 1. As x goes to infinity, it's going to be 0. However, you can use it in the same fashion that you used that one. Remember, that was one of our shortcuts that helped us save a little bit of time when we found ourselves with a little bit more complicated limits. So let's say you had something like this. You can actually use this as a shortcut so that we don't have to actually do the work here, because you're going to be doing the same thing. Just like we did for this one, multiply top and bottom by 3, right? Because you're multiplying everything by 1. Top and bottom by 3. Use your substitution method. That's going to change that to, let's say, a y. And this is going to be a y. And I'm just making this really quickly. Once again, if you need the refresher, check out that video. But this looks just like this. And of course, using our properties of limits, we can take that 3 up front. This is going to be 3 times 0. So we always know that if it remotely resembles this, where it is an x up top and x up bottom, and you have different coefficients, it's going to be 0. The limit is going to be 0. You can use this as a shortcut, or you can just do the squeeze theorem and figure it out that way. And of course, by extension, this is going to be true for cosine as well, because it's also bounded. So because that was true, and cosine has the same exact bounds, you would do the same exact work, and you'll get the same exact result. If you have cosine x over x, that's also going to equal 0 as x goes to infinity. So you can use these as shortcuts whenever you have a function that looks similar to one of them. So you see that sometimes when you're trying to find the limits of your trig functions, you just kind of know, because that's how trig functions behave, like we saw in the previous section of this video. Sometimes you'll know because you have shortcuts. Sometimes you may not necessarily know, but you have the squeeze theorem that you can use. But then there's going to be other times in which you got to dig deep into your bag and use other tricks that you've used for other limits. And you'll see exactly what I'm talking about in our next section. Let's say we have the function x minus cosine x over x, and we're trying to find its limit as x goes to infinity. In some cases, like I just said, you're going to have to just use what you know. We know that limits have special properties, so let's just use our special properties. Let's break up this function and then break up its limits. So if we do that, we can get something like this. We have x minus cosine x, and each one of these gets an x because that's how fractions work. And of course, our properties of our limits tells us that this is actually going to equal the limit as x goes to infinity of x over x minus the limit as x goes to infinity of cosine x over x. This is just 1, right? This is just going to be 1, x divided by x. And what's the limit of a constant? The limit of a constant is just going to be that same constant, 1. And we just talked about this in the previous section. What is this limit? This is going to be 0, which means that this limit is going to be 1. Use what you know. There's not just one way to find these limits. Sometimes you have to dig deep, and even using basic principles of your limits is going to be a viable option for you. Let's say you had a function that looks like this. You're trying to find the limit as x goes to infinity of sine of 1 over x. What do you have to do here? Once again, don't be afraid to use your basic limit properties. Your limit properties means that, remember we had something like this, right? If you have the limit of a function of x, right, you can actually, let's say x goes to infinity, you can actually do the function, right, of that limit of x. This is a viable property of your limits. You can throw your limit into the actual function. Let's do that in this case. This tells us that we can now have sine of our limit as x goes to infinity of 1 over x. Now we know what this is. We just talked about that as well. The limit of 1 over x as x goes to infinity is going to be what? 0. So you have this equals sine of 0. And what's sine of 0? Well, sine of 0 is going to be 0. Your limit properties will probably save you a lot more than you think. Let's say we had something like this. We have 4 over 3x minus sine x, and we want to find its limit as x goes to infinity. Use what you know. Now, this may look a little daunting because it doesn't look like something that we've done before, but we have done something very similar. We actually talked about this when you're doing your polynomial limits, your rational polynomial limits. If you recall, what were the steps that we had to do the long way, not the short way, not the shortcuts that we talked about, but the long way of doing those types of limits. Let's say you have something like this. The limit of x plus 1 over x squared minus x plus 2 as x goes to some, let's say infinity, right? We said that if you were to do this, you would then, the long way, not the shortcut way, you would divide by the x with the highest power. Divide top and bottom by the x with the highest power. That would be this x squared, which meant that you have x over x squared plus 1 over x squared all over x squared over x squared minus x over x squared plus 2 over x squared. And then we found the limit of this as x goes to infinity. This was the long way of doing our rational polynomial limits. We're going to dig this up and use the same method to handle this one. We're going to see that it helps us to find its limit quite easily. So what is the x with the highest power here? It's going to be this 3x. So we're going to have this x being something that we're going to divide by everything here, right? So we're going to have the limit as x goes to infinity, and we're going to divide everything by that x. So it's going to be 4 over x over 3x over x minus sine x over x. Now we're going to find a limit of all of this. And using the properties of limits, you get something like this. The limit of 4 over x as x goes to infinity all over the limit of 3x over x as x goes to infinity minus the limit as x goes to infinity of sine x over x. This is what our property tells us. Now, by finding these individual limits, we know that this is going to be what? Well, this is going to just be 0, right? 0 because 4 over x is going to be the same as 1 over x. And as x goes to infinity, it all goes to 0. This is going to be what? 3, right? Because that's a constant. The limit of a constant is always going to be that constant. And we already talked about what this was from the first part. Well, not the first part, but the second part of our video. Sine x over x is going to be 0 as x goes to infinity, which means that you have 0 over 3, which ultimately equals 0. Well, I hope you were able to follow along with today's video and hope you now see that you have a lot of options when you're trying to find your trig limits as x goes to infinity. However, if you have any questions about what we saw today or even on homework, you can always put in the comment box below or visit me on my Facebook page at Tutor Me Sempai and tell me all about it there. If you hadn't done so already, remember to hit that like. It surely helps the channel by letting YouTube know that you found a video helpful. And if you found a video helpful, so can someone else. So leave a like, hit the notification bell, smash the subscribe button, and share this video with a friend. Well, that's all the time I have for today. I'm really hoping this helped with your homework, and I'm looking forward to seeing you again next week. I'm Courtney, here's your playlist, and this has been another session of Tutor Me Sempai.